This QuickLearn Bullet explains three key yield measures for a bond: current yield, yield to maturity, and yield to call. Perhaps the easiest bond yield measure is that of current yield. This is simply the coupon divided by the price in percentage, as shown in this formula here. This measure is intended to give a more accurate reflection of the return on investment arising from the coupons when a bond is trading above or below par. So a coupon of 8% paid annually on a bond trading at 80 instead of par results in a current yield of 10%, an entirely intuitive result since you would invest $80 to purchase this bond and would receive $8 in coupon annually. Similarly, if this bond trades at a price of 133.3 relative to par, its current yield would be 6%, as per the calculation appearing now. Also an intuitive result, since the $8 coupon can be visualized as representing $6 on the first $100 spent and another $2 on the additional 33.33. The relationships described in this table will always hold. When the bond's price exceeds par, the current yield will be less than the coupon. When price equals par, the current yield equals the coupon. And finally, when price is below par, the current yield exceeds the coupon. A more difficult concept is that of yield to maturity. Returning to the example of the 8% bond trading at 80, we now assume this bond matures in 10 years exactly. The 10% current yield, while incorporating to some degree the benefit of purchasing the bond at a discount to its face value, does not account for the $20 of additional capital gain at maturity relative to the initial investment of 80. The rate function in Excel allows us to calculate precisely the instrument's so-called yield to maturity, using as inputs the price of the bond, its coupon, the number of remaining periods until maturity, and the face value. Yield to maturity is perhaps the metric most commonly used to enable a comparison of two bonds that have the same maturity but different coupons and/or price. To illustrate, assume bonds A and B have a semi-annual payment frequency, that bond A pays a 5% coupon and trades at 105, and that bond B pays a 4% coupon and trades at 96. The question is whether the $9 additional paid to purchase bond A represent greater or lesser value on a PV basis than the additional 1% coupon this bond delivers annually, also on a PV basis. This comparison is tricky because it needs to reflect the time value of money and the different entry prices under the two bonds. The rate function in Excel reveals that bond A's yield to maturity is 4.38%, which lags bond B's 4.5% yield to maturity by some 12 basis points. Assuming you perceive no differences in the two bonds' credit quality or liquidity or other factors that explain this difference, you are tempted to purchase bond B rather than bond A. We have explained yield to maturity in non-technical terms, but now provide a formal definition. Remembering that any cash flow has a PV equal to its size, discounted appropriately, we can write for the 10-year 8% bond priced at 80 the following equation. The price of 80 equals the $8 cash flow at the end of 1 year, discounted at 1 plus y, plus the next $8 coupon at the end of 2 years, over 1 plus y squared, and so on, up to the last cash flow consisting of $100 of principal plus the last coupon of 8, discounted at 1 plus y to the power 10 on account of the 10-year maturity. The value of y that satisfies this equation is the bond's yield to maturity. It is that single rate which, when inserted into each denominator, brings the bond's price under the formula in line with its observed price in the marketplace. If another bond pays a coupon of 8% semi-annually, but has the same terms otherwise, the above formula would be rewritten as follows. Note the $4 of coupon in each period, the y over 2 instead of y in each discount factor, and finally the 20 cash flows rather than just 10 over the life of the bond. We now write the above formula in its most general form. For a bond with a maturity of n years, a payment frequency of F, a coupon of C dollars per 100 of face value, and a price of PR, we write this expression here. The above formula leads to the following important observations. First, for a given bond and a given coupon, as the price rises, yield to maturity falls, and vice versa. Second, if a bond is trading above par, its yield to maturity is lower than its coupon, and vice versa if it is trading at a discount to par. And third, if two bonds are trading at an equal discount to par and have the same coupon and the same payment frequency, the one with the longer maturity will have the lower yield to maturity, and vice versa for bonds trading at an equal premium to par. Our earlier table can now be expanded as follows. When the bond's price exceeds par, yield to maturity is less than current yield, which of course, as we know, is less than the coupon. When the price equals par, all three of these become equal. And finally, if the price is below par, then yield to maturity is greater than current yield, which is greater than the coupon. Yield to maturity has one key drawback. Remember that in the formula defining yield to maturity, reproduced now, we use the same single value for y in each denominator, reflecting the difference in the time of each cash flow simply by raising each denominator to a different power. Yet the use of the same discounting rate in the denominator, and specifically the constant value of y, suggests a flat yield curve, which is almost never the case. A more correct approach would be to use gradually increasing values for y when the curve is upward sloping, and gradually decreasing values when the curve is inverted. But then our equation would contain several variables and so would have an infinite number of solutions. For this reason, the convention has been adopted to use a single value for all discounting rates, despite the limitations of this approach. A more advanced approach is to use an individualized risk-free rate for each cash flow, and then add to that a constant credit spread for all cash flows, such that the sum of cash flow PVs equals the bond's observed price. This is referred to as the Z-spread and is discussed in detail in a dedicated QuickLearn Bullet. We complete this discussion of yield to maturity and bond yield measures by introducing the closely related concept of yield to call. Return to the 8% 10-year bond priced at 80 and assume that this bond may be called, i.e. prepaid, by the issuer 5 years before maturity at par. The holder would normally be pleased to have the issuer call the bond on its call date, since the $20 discount to par would then be earned under this scenario after only 5 years instead of the anticipated 10 years, providing a significant boost to the total return for the holding period. Yield to call measures the bond's yield to maturity, assuming the bond is called on its call date, and otherwise works exactly like yield to maturity, except that the number of periods remaining until the call date now replaces the number of periods until maturity. This concludes this QuickLearn Bullet on bond yield measures.